Now let's design a function recursively to find the Fibonacci numbers in the Fibonacci series. Fibonacci series is defined in math as follows. The sequence is found that the current number in the sequence at position n is a sum of two previous numbers. So the seed value to begin with, let's use this one. The very at index 0 we have a 0, and then next one is 1, then next number is adding the previous two ones, so 0 plus 1 is 1 and the like. So let's use this sequence, and then we find those Fibonacci series numbers. So begin with 0 and 1, next number is add the two previous ones, then it's a 1, and then next one number is adding to previous one, that's 2, and then next number is adding to previous was a 3, and the next number is adding to previous, just keep going on there. Then this is called the Fibonacci series. So we want to design a function called fib, and then provide position or index n. Then index n is this is a 0, index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and keep going on. So if I give a fib 12, what I expect is 144. If I give a fib 8, 21 is there. So let's design a function in doing so. So here we are going to design a function called fib. It returns an integer, and then at position int of the Fibonacci series. So Fibonacci series number. So assertion point is that if I call fib with 5, then it should be some number like here in 0, 1, 2, 3, 4, 5. It's a 5. 6, 7, 8. 8 is 21. So 5 is a 5. 8 is 21. Let's do one more time. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is 144. So Fibonacci 12 is 144. So let's design a function that satisfies those minimally 3 testing points. So recursive function design, int fib, int n is provided here. Fibonacci series, the position n is the size of the problem. Then let's apply the principle of designing recursive functions. So step 1, trivial size, solve directly. But here from the math, when size is 0, 0 is provided, size is 1, 1 is provided. So those two are two sitting numbers. Then after that, we just continue to develop the series by adding previous two numbers. So here, beginning with a 0 and 1, next number is adding 2, adding previous 2, adding previous 2, 1 and 2 is 3, previous 2 is a 5, 8, and so on. 13 is that's a Fibonacci series. So step 2 is assume that smaller size solution is available. So fib n minus 1, we know that. And then when you assume, you can assume not just the one solution. We could assume any number of solution is available as long as the size is less than n. That's step 2 actually. So far we have assumed only one solution available, but in the Fibonacci series we can assume more than one. So fib n minus 1 is available, or we could assume another size as long as it's a smaller size. Those solutions are available. Then step 3, solve for size n. So known fact is that size n, known fact is that if I add the two previous numbers, so previous number is fib n minus 1, and then one more previous one is fib n minus 2. So if we add 2, then we get current number. That's a known fact. It's a property of a Fibonacci series. But any smaller size solution, we can assume that that's step 2. So that's the findings. So let's translate it into program. So Fibonacci series, trivial case, if n is 0, then that is a 0. Else if n is 1, that is 1. Otherwise, the known fact is that if I add one previous one and then just two previous ones together, then that's the current positions value. That's a definition of a Fibonacci series. So assumption, those two are added together, then we get the solution for the current size. Let's verify that. Compile the program, run it, and those three test points are satisfied.